Okay. So this training came about more because it's quick and efficient. We're not going to go super deep, but we'll go deep if you want. And I developed this basically trying to solve maybe the three to five biggest problems that I see out there on Northwest. I don't support Mountain West a whole lot, but these are problems that I see throughout the industry. And so this is specifically tailored to reciprocating engines, mainly slow speeds, but a lot of the principles apply to the high speeds as well too. So got this great animation right here. This is a car engine, so it's a little different, but the concepts are the same. Two-stroke or four-stroke? How do you know that? Right. It's car engine, right? It's the valves, right? Dual overhead cam. Now they'll start to color code. So I showed this video to a bunch of second graders. They did a career day. And all they cared about was the vibration sensor and this animation and then this right here. And they spun it as fast as an actual Recip actually runs. Then they jumped up and down to see if they could get the vibration sensor to go up and down. They said, we're making an earthquake. So that's about as far as they got, but it seems like they understood it pretty well. So using fuel combustion, and it transfers thermochemical power to mechanical power, spins a crankshaft, and the crankshaft eventually gets to your car wheel and touches the pavement, okay? So ours are very similar. What are the three things that we need for combustion? You guys probably all know this, and I'm an easy teacher. It's right on the screen in front of you, right? So we need those three elements right there. We talk about the combustion window, and a lot of times you don't see a picture like this, okay? So on the very left right here is 100% fuel and 0% air. And our burn window is 14% fuel, 86% air. We call that upper explosive limit. The lower explosive limit is 5% and 95%, okay? Combustion happens inside that window. Everywhere else it won't, okay? So you guys all have your monitors with a LEL, and it'll be 10% of the lower explosive limit before we alarm, okay? What that means is if it's a rich burn, that's 1 part of fuel to 11 parts of air at stoichiometric, and stoichiometric is just a fancy name for theoretical or perfect or what we want. And that's 16 to 1. This is for natural gas. Gasoline is probably 9 to 1 or 10 to 1, okay? And then a lean mixture is 29 parts per air to 1 part of fuel. A lot of you have seen this burn curve right here, okay? If you can see the colors, there's NOx and CO that comes out of the exhaust. So right over here is the upper explosive limit, or what we call rich. Right over here is the lower explosive limit, or what we call lean, okay? Some of you have heard the term lean burn, not to be confused with clean burn, even though they sound the same. And the Ingersoll Rands, they call those rich burns. So the Ingersoll Rands, the 4 strokes, they'll probably combust around this ratio over here. And a lot of the 2 strokes will combust around here in the lean area. And then when you have high pressure fuel injection, they're trying to lean out even more, and they'll combust somewhere around here. So it's simple, less fuel, more air. Less fuel means less of those 6 pollutants that we're trying to diminish that come out of the exhaust, okay? Where do turbines run? They're ultra lean. I don't even know what the ratio is for a turbine, but it's ultra lean, so low NOx, right? They're using a whole bunch of air. That's why they're finicky, right? You might know the ratios. Yeah, but it's really, really lean, huh? Okay. They've probably taken it right to this point, and that's when you have flame out, it's probably because they're right on that edge, right? Yeah.
16 to 17%.
Yeah. So the comment was made 16 to 17% O2 oxygen. 50 parts to 1. Okay, that's what AI says. So I'm not going to question AI. It's got to be right. You know, a human had to put it into the computer to be right. So, okay, here's how you should look at an engine. I call this object cash flow. Okay, energy in, energy out. In your house, you want to spend the least amount of money and get the most amount of value. Okay, an engine is the same way. So an engine gobbles up fuel, which is going to cost us money or energy, and in return it compresses gas or fuel. Well, it's the same gas, natural gas, and it compresses that, pushes it down the pipeline. It goes to a meter station. We hand it off to the customer, and that's how we make money. So if you can use less fuel and compress more, you become more efficient. Okay. So the horsepower is made up here on the power cylinder side where gas is consumed, so it takes money. It spins that crankshaft. In integral engines, it's connected on the same crankshaft. In separables, they just use a coupling. And then that uses that energy. So one gives, one consumes, or driver and driven. Okay. Now you want those horsepowers to be the same. So at the horsepower, at the shaft, crankshaft, the horsepower, whatever is given is going to be consumed, and vice versa. Whatever is consumed, hopefully is there to be given. Okay. So there are some efficiency losses from the power cylinder head down to the crankshaft in the form of friction, mechanical hysteresis, and temperature. So in general, from the power cylinder top down to the crankshaft, it's probably about 85% efficient. And what that means is 15% of your energy is lost from the top down to your crankshaft, okay? And those factors, by the way, are in the PLC, and it's part of the mapping and everything like that, which you don't have to worry about. But there are ways that we can actually measure that on our engine analyzer. So that's kind of cool. And then what's consumed on the compressor side, there's also some friction losses and industry. And then what we've measured is usually about 95%. Okay. So 5% is lost from there. Starting. So this is what a typical Northwest pipeline HMI looks like. I don't know what Mountain West looks like. It might be something similar, maybe slightly different philosophies, but generally we start in remote auto because everything is automated. In remote auto, right here, you notice that you've got engine speed of 100% and torque of 90%. Where do those numbers come from? Who knows? Gas control, what was that?
Oh, I thought your torque would be a value of your thermal loss.
Oh, yeah. This is a set point the gas control puts in. Yeah. On another screen, it'll actually show you your horsepower, and we don't actually display those losses. So the engine speed is put in by gas control and the torque. Okay, and they're doing this remotely based on their nominations. Now the engine speed, you think they're typing in 100. It would be great if they could just type in 100, right? The engine speed actually comes from your pressures. So what they're doing, I don't have the other screen, they're just taking the discharge station pressure, putting it way high, like at 850 pounds, 900 pounds. The algorithm calculates and says, oh, that's about 95% speed that I need out of this engine, or 100% speed. So it seems odd and counterintuitive that a pressure set point changes your speed, okay? But that's what's going on at gas control. Torque, as I understand, they just type in 90, okay? He's simple enough. When you go to local auto, that's slightly different. You see how we've got these pressures? It would be great if we just had engine speed and typed in 100. Same thing, you as an operator can put an extra high discharge or an extra low discharge. And what you're saying is, hey, engine, catch up to the suction and discharge. Give me a great big spread or differential, or the correct term is actually ratio. And you do your thing, okay? So this also will give you 100% speed. And then you can put in your torque manually right there. In local manual, this is where you control it right at the engine. But gas control cannot touch any buttons. And so over here, you can actually put load step in. And load step is another way of saying torque. So reciprocating engines have load steps. And what that means is pieces of volume you can open and close. They will add or take away the torque on the compressor on what it's asking for. One of the reasons that people like reciprocating compressors is they're flexible in their volume, and you can ask a little bit more or a little bit less, and you're not hurting the driver so much, okay? Turbines, do they act that way? So turbines usually like to be loaded up really, really well. So the way I look at this is these recips, especially these old recips, they're kind of like mules or donkeys. They can just work hard. You can feed them garbage. You can push them. They're gonna just keep working, and turbines are Clydesdales. They want their hair combed. They cost a whole lot of money, and they will run perfectly at what they're supposed to do. And they look good on all the commercials during the Super Bowl, right? Neither one is good, better, or worse than the other. They just do different things and different functions, okay? So that's how we start right here. So question to the group. When we are taking a resonance analysis or wind rock analysis, which mode should we be in? Local. Yeah, so the comment was made local. Go ahead. Oh, I thought there was a question over here. So many times we're in remote auto. That's okay as long as you're cranked up and gas control is not going to fiddle with anything. But what happens when your load changes in the middle of your analysis? Right? It's worth just starting over. Thanks for saying that. Exactly. So especially if someone else is analyzing your data. So haven't helped the person analyzing your data that didn't get the memo that load changed. Because now me, Romero, or Dustin's in a position of saying, you are in load step 2. Oh no, it thinks it's in load step 8 or load step 9. You have a broken unloader, right? So that's one of the reasons we put it in local manual, just so you can lock it down and you can manipulate the engine the way you want, okay? Questions with that? I believe it's part of OpQual to do all 3 modes. Maybe not. Maybe that's just tribal knowledge you just learn. Okay. Do that. Yeah. They'll, as long as you're pushing gas to them and they need it, they'll probably be fine, and then just switch it over to remote in the end. I mean, if you cause a glut or you're pushing up against something, then maybe they'll holler at you. But my experience is they've always been really good about letting you have it. So there's that. Mountain West, chime in. What is your guys' philosophy? What do you guys do? What does it look like? Okay.
Talk to gas.
Okay.
Stick it in local manual, that way it's not changing.
Okay. Sounds good. All right. So starting. This is just a game of RPM versus fuel. Okay. You see that little drawing I have at the bottom? You're just kicking a motorcycle. The harder you kick it, the more chance you have of a good start. Okay. Now, there's a few factors. Earlier this morning, we talked about fuel or oil temperature. What if your oil's cold? Might want to kick it harder, right? What if you're not combusting? What if you're not producing enough air manifold pressure to sustain the turbo? Okay. So this is a list right here on the start screen where the engine starts to preloop, then the turbo's preloop and it gets up to a specified pressure under a certain amount of time. Cylinder preloop and then turbo assist in this case. So this is Pocatello and the turbo assist. This sprays air into the turbocharger and it sprays it into the air side. It sprays into both sides. Do you know at soda, Toku? Yeah. I think it's in the air side that it's spraying it. And what that does is it causes the turbo to turn without combustion until it can finally combust and sustain. Okay. So another way of doing starts is with ring gear starters. So Chehalis, Washougal, others, Oregon City, and what this is just rings that spin the flywheel, just hooked to it and it just spins it. Okay. What kind of air starters do you guys have in Mountain West?
We have one, yes, it's
Okay.
there.
All right. And then there's another way where they just spray air into the power cylinder. So you're spraying air into the power cylinder and it just starts going up and down just by spraying air, and spark and fuel haven't even been introduced yet. You're just moving it back and forth, okay? That's the equivalent of push starting an old car, right? Until you can finally get it going, okay? So that's what we're doing. So the name of the game is more energy, more kick gets you a higher percentage of start, okay? So more air, more power. Once we start doing that, we want to hit 35 RPM. Starting air hits, like I said, or yeah, turbo assist, starting air. Then we light up, so the ignition starts to spark. And then we introduce fuel after that. What would happen if we did fuel first, then spark? Might have some problems with pressure and too much, and you can't control it. So spark first, then fuel. And I don't know what that exact delay is. We have that in there. So now you're combusting. This is going up and down, and you're starting to produce heat. When you produce heat, the exhaust goes where? To the turbo. And when I say turbocharger, there's a hot side and a cold side. So the hot side of the turbo spins a wheel, and connected to that is on the air side. So this is the air intake, and it starts to suck in air that goes into your power cylinder, and then you are sustaining combustion. Okay. So that's how that works. On Fast and Furious, whoever's watched those shows and they push the nitrous oxide, what's that doing? Anyone? AI might tell us.
Different type, different fuel in the inlet.
Dumping fuel in the inlet? What did I hear over here? Yeah, okay. What it does, it actually cools the air, super cools the air, so you're dumping more air in. And then it takes off like a power band. So at least that's what AI Google told me. So maybe Fast and Furious has something else going on. What's that?
That makes the lights go blue.
Oh, yeah, it does. Yeah, because you're going so fast, huh? That's right. Yeah. Okay, questions about starting. That's kind of the idea and the theory behind it. Just like turbines, it sounds like recips, we have headaches with starting. There's all sorts of parameters and things that can happen, right? But in general, air, fuel, ignition. So if you know you got ignition, and a lot of times we question, but if you know you got ignition, what are the other two things you're going to troubleshoot? Air and fuel, right? So the air is pretty simple, unless you got clogged filters. You're probably going to know that because you walk past them every day. There could be ice on the filters. Maybe a bird made a nest there that you didn't know over the weekend, you know? So it could be clogged up. Turbos slowly over time could get dirty or something like that. The wastegate could be broken, so you're dumping a lot of energy without using it. So a lot of times fuel is what you're going to look at, right? Governor, combustion problems. So fuel might be some of your go-to, but you guys got stories galore of things that you found that would be odd that you wouldn't think about. And then when you dial it back, it's going to be one of those three: ignition, fuel, air. Okay. Here's a trend. So you can also do this on Pi Data Viewer that Edon showed you. This is on the HMI. We have that capability. So it's just there. It's quick, right? But here's the lack of air manifold pressure, which I call the sustaining life of combustion. So how do you know your turbo's working? Well, what if my probes are bad? So one of our station, both our probes are bad, so we can't see them spin. So as a surrogate, we know they're spinning. We think they're pretty healthy. We've looked at them, but our air manifold is going up on both the turbos and it's the same. So we just make the assumption the turbos are good until we can get these RPMs, the probes fixed, right? It's actually a ground fault that's causing those things. So bad combustion, dirty air filters, weak turbocharger, lack of fuel, bypass, bad spark, all the things we just talked about. The trend tells the tale. So hopefully with Ryan's presentations, Edon's, mine, the trend tells the tale. So if you can trend it, you can start surmising what's kind of going on. Okay. Here's what a turbocharger does. You guys have seen pictures like this. So it's just a loop, goes around in a circle. Here's the hot side. Here's the cold side. So combustion or hot air, exhaust, excuse me, comes through here, spins this wheel right there. In turn, this spins that, compresses the air. And sometimes, and then a lot of times since you compress air, it gets hot. So that's why we have intercoolers. And some of you have cooling water fans or scavenging air fans, I think, where it will actually cool. It's a cooler around the air, so that colder temperature goes into the combustion process and you get a better combustion. So some people call that boost. I'm wrong when I say free energy. Do you see how I have that in quotes? Look at my little disclaimer for all those that watch the car shows, and we don't have Fred here. He says he restores Impalas. The small note is turbocharger is not free energy. It comes at a thermodynamic cost, but it's available and not used, so you might as well harness it. Okay. Every once in a while, you'll say it's free energy. I mean, if you go to a dealership and they got this new turbo, they don't know what they're talking about. They say it's free energy. Okay. Every good mechanic will be like, hold on, it costs a little bit. Okay. So here's the air path. Ambient goes to filter. You're going to have a little bit of loss through a filter. And we're talking in inches of water or inches of mercury. Mercury. Okay. And then you're going to compress it. Also, the temperature goes up, goes through a cooler, a little bit of loss. Engine going to go through there and then go to the turbo. Here's that wastegate I'm talking about. The reason they call it wastegate is you're just wasting the energy or you're sending it to waste. So you're choosing not to harness that energy on your next combustion process. Okay. There's reasons why we would do that. But in general, you want everything you can get. Okay. So that's the turbine side of it. Sometimes there's a treatment silencer and then back to ambient. Okay. This is in the WIMS procedure, just another way of looking at what I just explained. Okay. Questions about turbos, starting, combustion, anything? I'm sure most of this group very well versed on that. So one thing I wanted to cover is governor errors, and I'm going to cruise through this one because I think we talked about last year as well too. So governor errors, we have Gov 10s and Gov 20s, all except for Caldwell and Baker, where you guys have Woodwards and we're making them run, and we have the brains that we have spared out, and so far so good,
The
right?
magic just happens, it comes out.
And it still works. Yeah, it's just
You don't
magic.
touch anything in there.
Yeah. So here's just a connection. Since all your computers are locked down, these connections to your USB don't seem to work anymore. Here's the hack of the day. All right. F1, F2 setup on your governor screen. Okay, that's in the manual right there. So instead of fiddling with your COM port for 3 hours, just do that little combination and go in there if you have to change. Hopefully you're not changing governor settings. If you are, other things are wrong. They should have been commissioned. They are commissioned. They work. Doesn't mean we can't look at them and question them, right? But, and if you know what you're doing, fine, go do it. Here's the configuration settings. This isn't a governor training, but just know they exist. They can be tuned if you want. And most of my experiences is if you're fiddling with the governor, you're masking over something else that wasn't happening before. Okay, that makes sense. Here's just the terminal program. One thing about the trouble alarm, well, I'll get to that. We do, in our code, we do have a fuel stop permissive timer, and what that means, from 30 to 60 seconds, we want to ensure that the pressure, a proper blowdown in the fuel pipe happens. So it's 3 PSI within 30 seconds. So TLAs have this problem. So POC and soda, and I think we've fixed that. I haven't had a call for years on that. Just a little bit gets trapped and doesn't blow down for the next start. The fuel stop permissive is 8 minutes to account for a blowdown. Yeah, that's what I was just talking about. This might even be, yeah, Pocatello station. That right there just had a little bit trapped, and you can't duplicate this. It's only the way that the power cylinders landed when it stopped based on the volume. And so, and there's no bleed off. There's no AMONT bleed off on these actual TLAs. The other ones I think have an AMONT bleed off or something of the sort. If you haven't had the problem, then don't worry about it. Just know about that. These trend screens, we've talked about them, engine help. Between Lance, me, and Clint, we've pretty much, if we don't see a tag on these, typical, these are the canned trend screens on there, we'll usually put it in there, and it's RPM, air manifold pressure, turbo, all the stuff that sustains life for combustion. Here's one. So this is the main one I want to talk about. You guys have ever gotten the Gov 10, Gov 50 alarm, right? So your first reaction is, oh no, the governor restricted me, and it must be something in the governor, right? That's how I thought it was working when we commissioned these things. And thankfully, you guys don't have the governors, and so you don't get this alarm, right? But maybe you get other alarms. What we found by looking at the manual is the governor reacted to not seeing the speed or a bad start, throws out an alarm after the fact, and was not the cause of it. So slowly, if I'm at a station, I'll just make that auto reset just so it doesn't mislead a good technician trying to troubleshoot their engine. So every once in a while, you'll see those, and it's in reaction. It's not a cause, is what we found. So Pocatello soda, every once in a while, you'll see those as well.
Does it throw an alarm on the governor? When you get the Gov 10 trouble alarm? Like, I can't find, when we get that on the HMI, hook up to the governor, I can't find any alarms.
I don't think it is on the governor screen. Yeah, that's what's, I mean, it's not state of the art.
Yeah.
Go ahead. Yeah, yeah, it wanted a certain RPM in a certain amount of seconds, and the engine already knocked silly, and then the governor goes, "Oh, I didn't see the RPM." Throw an alarm.
And then so after that, like, I'll just.
Oh, really? Okay.
That's the only way to get.
Maybe a hard reset. Yeah, I see what you're saying. Yeah, go into the PLC and have one of us just click it and get it. Oh, okay. Yeah, so there isn't one on the actual screen that says that. Actually, it might actually say this, stop low RPM right there, but I don't know if there's an acknowledge reset on there. Okay, so just know about that. We'll cruise along. Well, fuel start permissive if it didn't get, if the RPM is below 125, but you threw a whole bunch of pressure at it, you'll get a fuel start permissive. That's in the PLC. That's what's going on. Usually that's because your starting air or gas control didn't wait for the starting air to pump up. So Moab, Pocatello, soda, you got those starting air volume tanks and you're just trying to kick the motorcycle as hard as you can. And it'll work at 247, but it won't work at 235 or something. But some days it'll work at 235. So that's usually what's going on when that happens. Just didn't get enough.
And that's
Kick.
actually pushing the power piston.
Yeah,
Okay.
on the TLAs, yeah. Yeah, they're spraying into the power piston, and so they have a starting air valve that goes into the side of the piston, and yeah.
I didn't think you had anything like that anymore.
Yeah, a lot, and we actually even have a temperature probe on those starting air valves. So if those get hot, you know, especially while you're combusting or running, if those get hot, you know, you got a leak going back in. Okay. We'll skip all that. A lot of permissives. Okay. Torque and fuel flow. All right, when you're looking at this screen right here, and Mountain West might look a little bit different. You see how I see the speed of 300 and torque at 96. And then I've got an operating torque set point, or SP. That's different. Then I've got allowable torque. Then I've got horsepower. So why do we use torque and not horsepower? Anyone? Why do we always talk about torque?
Torque is just
Yeah, exactly.
Something that gas control can relate to, your operator unit,
Yeah.
basically.
It's just because how it was programmed long ago, and torque is a better indicator of, like Eric said, you have rated speed baked into there. So here's the actual formula. It's horsepower actual divided by horsepower rated times horsepower rated divided by RPM actual. So it's just that ratio. So it's 4 parameters into 1 instead of just horsepower being 1. Okay. So it has a limiting factor. You're 100% of your capacity. It's another way of looking at it.
Yeah.
Yeah. So that's what torque and speed are. Do you see these right here? Now, we don't really use these a lot, but this is actually a performance parameter. We have fuel usage predicted, fuel gas usage actual. Okay. Do you see the units? 1,000 BTU per horsepower hour on there. What the heck does that mean? All that is energy in versus the energy you're getting out. We just confused you by putting BTU divided by horsepower. What we should have done is fuel in, compressor compressed, so throughput compressed, right? So it's just generating horsepower, and here's how much fuel it took you. Maybe that's an easier way of putting that, okay? So this is a performance parameter, and it's predicted off some curves that we put into the PLC. Most of them are correct. There's a couple that might be slightly off. And then we alarm off it, so it might be annoying. Do I have gas controllers in here? Okay.
They left.
All right. Darn. We had this meeting so we could talk about torque. No. They'll listen in later on. So you're all doing a great job, gas controllers. When we run a reciprocating engine at low torque, what happens to your fuel? Go up or down? Goes up. Yeah. So in a car, when you let off the gas, your fuel flow should go down, right? Reciprocating engine, they actually are more fuel efficient when your pedal is to the metal. So when they're as high as possible. So do you see how this is 7.3 right here? If that torque goes down to 70%, that's going to turn into an 8.3 or a 9.3 right there. And all it's saying is you're burning more fuel for less horsepower you're getting out of it. Okay. So we do alarm off this. We don't act on it because gas control controls this, they got their nominations, they see a bigger picture than we're actually seeing. But if you do have your preference, pedal to the metal cranked up, right? Now, you just heard me say a little bit earlier, well, you can kick these things around like donkeys, right? They'll live, you know, they'll kind of go around, but the receipts are gonna come due. You're gonna have to be doing more maintenance later on, right? Whereas you couldn't even try that with a turbine. And, you know, the Clydesdale would be like, I need my oats, I need my nice apples, whatever, you know what I mean? So, just know those are things with a recip, okay? What about this right here, this discharge temp, this theoretical discharge temp and isentropic efficiency?
The gas temperature, the cylinder temperature. Are you asking for?
Yeah, I just switched to compressors, excuse me. Just while I'm on the screen. Yeah. And we'll talk about hot valves. This is just a little cheat. So walking up to your HMI or looking at this, and you know you're doing a windrock or a resonance analysis, and you see 10 degrees difference on here, you know something's hot in your compressor. You're cheap. And then you're going to walk up with the earphones and you're going to put it on there. I told you, right? And then you're going to put the resonance on there and then it will show up again. Okay. Three points of information. What this tells you is suction temperature, discharge temperature, that's measured. This is theoretical discharge temp. It shouldn't say theoretical. They say that because it's calculated. This should say isentropic discharge temperature. And what that means is if everything was perfect in an ideal world, then this is what your temperature would be. But because of friction and temperature losses and hysteresis, your temperature through all those losses is now 20 degrees higher than what ideal or perfect is. Ideal and perfect never exists in thermodynamics. In our world, there's always some losses. So they do that divided by that, and they say that's isentropic efficiency. And we won't get into entropy, but who knows what entropy is? Yes, we will get in. Yeah. What's that?
Decay.
Decay. Yeah. Measure of randomness. It's just randomness or chaos. Or when a system just, it's like a blender. Whatever a blender does, the comparison before and after, it's just chaos and loss of energy. Okay. If there's anyone listening to this later on, that's not a very good thermodynamic explanation, but that's the way I understand it, okay? So this right here, can you see that a 2-degree temperature difference is a 3% loss in efficiency on that? This is thermal efficiency, okay? So we just did that calculation for you on there. It's just kind of a nice little cheat, okay? What are some other things you notice on this screen? Who's confused with operating torque set point and allowable torque? I am. Yeah, so why do we display that? If we're up to me, we wouldn't. Torque, what you're running at, and how high can I go? That's all you guys care about. So running torque and maximum allowable torque. I don't care about anything else. What this is this is the set point gas control puts in, but it does one more calculation. They put in like 90 and then it'll do a calculation said, oh, it can actually, it's usually never higher, it's lower. This is just a different snapshot. And this will say, hey, here's the set point it's supposed to get at. But then it's confusing because, oh, it's above my set point or below my set point based on different conditions, right? So if it were up to me, I'd just delete that right there. Just ignore it. Okay. So speaking of max allowable torque, this is where I want to ask the engine guys in the room here. So there are times where some engines can go above 100% torque. Okay. The ones on our pipeline are Mount Vernon 1, 2, Pocatello 4, Soda 4. These are Clark engines, and they can actually go up to 116% torque. Okay. Does that give jitters to anyone? Going above 100% torque? Yeah, it does to me as well. Chehalis, Washougal, and this is where I wish the gas controllers were in here. We can go up there safely, and the program allows it, and we have done it. many times. So for some reason, so Romero, Dustin chime in, Eric, if you guys know anyone else, maybe this would be a Lucas question as well too. Why did they make 116%, not the new 100? So why can we go up to 116%? I tried to look in my manuals. I found it a few years ago. I just couldn't find it for the training. Does anyone know?
Is it because there's no torque? In other words, it's running away.
Function of how much air you have.
Yeah. Yeah, so without damaging your engine, you can go up, and yes, it is a function of how much air you have. So for our engines, it derates below full RPM. So if you're running at 250 and it's 300 RPM, you're not going to be able to torque up completely. There's just a slight derate. I won't show you the formula. It's just got some factors in there. And then it derates above 70 degrees Fahrenheit, generally on these 7 engines. And so when it gets really hot on a summer day, you're going to have a hard time combusting anyway. So you're not going to over torque even more because you get erratic combustion. Okay. So and it takes the lower of both of those too and says you don't go below this or above this. So on a 30-degree morning, which might happen in Pocatello, right? 0 degrees, it's going to use, and you're at full RPM, it's going to go as high as it can on Pocatello 4 and Soda 4, which is 116% torque. So if the gas controllers are in the room, there might be some percentage of torque and flow that we could actually gain on our system that maybe we aren't using on there. So a lot of folks get jitters going above there, but it's not every engine, and the controls will limit you right at 100% torque. So I was told it was just Cooper engines that could do that, but I looked at our code on these 3 as well too, and then ran some of the calculations, and these 3 can go up as well too. So did you guys know that about Caldwell 4 and Baker 4? They can go up, but the other 3 engines next to it can't. So if I were in a gas controller situation, I would be confused, or I maybe wouldn't even know, oh, these 3 right next to it can only go up to 100, but the one next to it can go to 116. So it's probably at 100 a lot. Yeah. Mm-hmm. Just thought I'd bring that part up. Questions to this point? Good on time? Okay. Fuel valves and balancing. Okay. So here's what's going on in this little cylinder right here. If you look to the right. And I tried to speed it up as fast as the software would go, but this particular software wouldn't even go up to 250 RPM. But it's going so fast your computer can't even keep up. And we call that a slow speed. Okay. So right over here, what's this called? Peak firing pressure. Okay. What's this called? Exhaust blowdown. What about this? Yeah, running compression. Yeah. Sometimes it's expansion and recompression, all these other terms and everything, but looking at this, you can call it whatever you want. So right here, what's this little blip right here? Spark. How do you know it's spark? It says it at the bottom, but also Dustin was probably trained to look at where it's happening, right? What if I sparked over here? Would I light off? Yeah, it has to be at a certain time, right? Right here, this is at probably maybe 8 degrees before top dead center. 8 degrees before top dead center is the same as saying 352 degrees. Okay. So it fires before top dead center. Why do we fire before top dead center? Well, mainly because we can. But what if we fired too early before top dead center? You break stuff. Why would you break stuff? Okay. I'll try to put this, maybe you can see it in the camera, I don't know. So this right here, and I think a light comes on, maybe it doesn't. A light's supposed to come on when it sparks. Oh, there you go. Did you see that? Okay. So this right here, if I fire too early and I'm moving up right here and compression starts to push this thing down, or peak pressure, it starts pushing on this crankshaft when it's spinning one way. And this little moment arm, if it's too early, it's going to push down on the crankshaft and you got all sorts of damage happening. So you're essentially pedaling backwards when you're trying to go uphill, right? So that's why we sparked at that time. Mainly because we can. If you look at the pressures right here, the pressure's not that high, and combustion starts to happen. And then right over here around 22 degrees, 18 to 22 degrees, that's where we get peak pressure. And then finally we get the kick or the push that goes down on the crankshaft. And that's where the horsepower is made. Okay. So the higher this pressure, the higher the force pushing down onto the crankshaft, right? And you want it to be spinning. You don't want to hit it right on top. Okay. So what's this right here?
Fuel valve opener closing.
Yep,
You'll be closing on this one.
fuel valve closing. So see these bands, fuel open, fuel close, intake open, intake closed, exhaust open and exhaust close. What's the difference between a 2-stroke and a 4-stroke? So see this animation versus this right here? What's the difference?
2-stroke fires here with 2 strokes, 4-stroke fires every 4 strokes.
Yeah, yeah. So the comment was made, 2 strokes fires, you get a power kick every 2 strokes. 4-stroke is a power kick every 4 strokes. A 4-stroke just breathes better. So it just does one more breath and then it fires. And so the mixing happens a little bit better. So they're generally cleaner. And 2 strokes, you just throw fuel at it and it just combusts when it can, essentially. Maybe that's a loose way of saying it, but that's how I understand it. At least that's what you do with the motorcycle. You just go, right? Okay, and then there's ultrasonics as well too. So one is vibration, one is ultrasonic, which is, you know, Superman hearing, and then this is the pressure right here. So that's what's going on in a power cylinder. And when these things happen matter. So the number one mistake we make is timing. We don't time our engine correctly. And what I mean by that is when we're taking data. Our engines are timed automatically correctly, except for when they aren't, but our controls are timed correctly. If you have this timed off, the picture is going to look like a different picture, and you can't get any diagnoses off there. So the number one mistake we make, timing's off. The number one thing you need is timing has to be correct. Okay. So doing a little math, there's no formulas. So if this piston diameter is 18 inches, that's a surface area of 56 square inches, 250 RPMs. That is 4 cycles per second, to give you an idea how fast that's happening. And if it combusts at 500 PSI, which is around that, that's 900 pounds of force pushing down 4 times a second. And then if you have 6 cylinders, that's galloping 900 pounds of force up and down 4 times a second. So that's essentially 6 elephants jumping up and down 4 times a second, and that's happening inside your engine. So hopefully that gives you a good appreciation of the forces involved inside these reciprocating compression, these reciprocating engines. So if you have a loose rod or a loose pin or something loose in there, you think you're going to see that with 900 pounds of force going 4 times a second, it's going to show up, right? So a vibration, hopefully you'll see something for real on there. So and that's a small engine, that's a TLA6. So you have something like Chehalis or Soda Springs, that's, you know, 20 elephants jumping up and down, you know, a whole lot more forces.
I don't want to nitpick your math.
I get it.
If your diameter is 18 inches, Isn't surface area pi r squared? We still use that?
Yeah, it's pi r squared. I get it wrong.
If your R is 9, square that to 81. 81 times pi puts you.
Maybe I did that math wrong. Okay. I'll double check that. Thank you. And you can nitpick my math. Yeah. Should have had that correct if I didn't have it correct. I'll look at it. Yeah. I did it last night after the meeting, so I might have missed something, but I'll double check that. Thanks for that. Yeah. Yeah, all right. Take off. Yeah. Thanks for coming.
Appreciate that.
Yeah. Travel safely. Okay. So what are these right here? You guys already mentioned fuel valves. What do you notice about the red one? Okay. What about this blue one?
It's getting bad. It's
Chattery?
It could be crossed off.
Okay. You might have a double tap on that valve and this one's really, really loud. So what does it say about the timing? Is it happening where it's supposed to be? This dotted line right here, for the most part. So it's happening pretty much where it's supposed to be. But if I'm having a hard time balancing, or I've got combustion problems, or I'm not starting, which fuel valves am I gonna look at? Yeah. Okay. So what about this one? Tell me about the fuel valves. Yeah, timing's off. So, and when you say timing, it's the timing of the fuel valve, not the timing of the engine.
What's your data?
Your data is wrong. Yeah. Yeah, so, this one is way early, 24 degrees early. It's all over the place. So you've either got something broken or someone adjusted them differently and didn't take heed to make them all the same. Okay. What's this? Some noise around the combustion. So here's where combustion happens. Could have been that too, yeah. If you see that 3 times in a row, then you got a problem. If it's once, then you might question it, okay? So here's what the fuel valve adjustments look like. So, if you are left of this line, so when I say this line, it's that line right there. That's when the fuel valve is supposed to close. First of all, it's closing early, which means you're getting less fuel. And less fuel means what? Well, it's fine if all the other assemblies are getting less fuel too. Not really fine, but at least you're not going to be chasing your tail. But if one of them is getting less fuel, so it's not combusting as well as the others. It might be going high, might be going low. So as far as fuel valves go, if it's left of that line, that means it's recession. And what I mean by recession, it's worn right here, either on the stem or on the valve seat right there. Or the guy who set them up too tight. So of course you don't want to go change out a fuel valve, so you might just loosen one and see if you can get by. But again, the receipts are going to come due and you can't just keep doing that. So you got to make sure that the valve seats are not worn, okay? And then right is lash, which would be too loose. So it's possible that it's just too loose or that nut came loose. Or if you have a hydraulic lifter that is just mush in there and it's just going back and forth and it looks like it's loose, but the actual hydraulic lifter is not working. Solid lifters, I don't know how that looks on there. Do you guys have comments with that? Do you guys deal with these? Yeah. Okay. Threw them in the trash.
No, we have a lot of problems with fuel valves unrelated.
Yeah, unrelated.
Oh, okay. All right. So I should mention ours are all open chamber carbureted. We don't have any high pressure fuel injection. So this is old school. Okay. So our general rule is 8 degrees. If we see 8 degrees difference, then we're pulling a valve. That's not in a WIMS procedure. Maybe one day it could be or should be. The general rule, if you're seeing that type of movement, pull the valve. Okay. Should we take a little break?
Better push through, we got 2 clogged out.
Okay, all right. We'll do it. Okay. So any questions with fuel valves? Okay, how about ignition timing? Do we mess with ignition timing?
Sometimes.
Sometimes we do. We can. And in some times, some places it's good to do it if you know what you're doing, okay? So here's what ignition timing does. The blue trace is normal. That's 10 degrees before top dead center. The red is retarded 2 degrees, which is -8 degrees before top dead center. So just a little bit later. And then the gray is advanced to 2 degrees to -12. So before or later than normal, okay? This is what it does to your peak pressures. So if you advance it too much, like I tried to show over here, this peak pressure gets right at top dead center and you're kicking right onto that crankshaft and problems will happen. I'm not showing you what pre-ignition looks like. Pre-ignition is when this pressure lights off up here and it's very, very rare. And then you have a real big combustion event right on top of your crankshaft. Yeah.
We've had.
Did you hear it?
You don't hear it.
Apparently you don't hear it. Yeah.
Detonation, you hear.
You just see it when you open it up.
You see it.
Yeah. Yeah, you see the consequences. Well put. So look at the exhaust pressures and temperatures. Do you see how that red one is a little bit higher, a little bit more pressure? So if I have, that's just a tiny amount of pressure, but when you're desperate, right? So that little bit of pressure goes into the turbo and you get just a little bit more air coming through on the next cycle. And if you're not passing emissions and you need a little bit more air and less NOx, this is something you could do, is retard the timing. Okay? Yeah, so that's something that will make your life a lot easier if you understand what you're doing. Okay? It's the same as leaning out an engine. So when you go to classes, changing timing and leaning an engine, the pressure trace reacts the same. Okay, so that's what it looks like right there. This banana shape is just a different way of looking at this pressure trace. Okay, so that's why we would advance or retard timing on our screens. Most of you probably haven't even seen these or don't even bother with them, which is great because that means they work. But every once in a while, if you have to, then you can tune it from here. And I think we need to make one more adjustment at Baker because it wasn't working last time and it's still on my list to update that. So when you put an input in there, it actually works.
Yeah.
Somehow. Yeah. Yeah.
Logic change it.
Yeah. We'll get that taken care of. So this way is advanced, this way is retarded, okay? Some engines you'll see that it's speed related, so up to 125 RPM. It's going to fire at 7 degrees before top dead center. And I would have liked these negatives and positives to be different because they're exactly the opposite from what the training says. So that's just how they were programmed, 22 years ago or something. So that's why I put that in here. Advanced is that way, retarded is that way. And then it will, on this particular engine, it will retard until the air manifold pressure gets up to about that, and then it will start to advance again. Okay. Usually those work, Shaylis, we have a few little headaches with that. But that's the way that's supposed to work. Okay. So here's just a list of what happens. So when you retard it, exhaust pressure increases and your NOx emissions decrease. So if that's what your permit is, do that with your testo beforehand so you know how much an increase or a decrease you're going to get. Okay.
By retarding, you're putting more heat to the turbo.
More air to the turbo. Yeah. More energy to the turbo, more flow. Yeah. Mhm. Okay. It's a little counterintuitive because when you're advancing, the peak pressure will actually go higher, which means higher temperature. Right? And so you think it would be just the opposite. You're getting higher temperature, which means you're getting more energy into the turbo, but it's actually the flow. So, questions with that? Comments? Okay. This all making sense? Clear as mud? Okay. All right. Exhaust temperatures, one of our favorite topics. Okay. Which one has the hottest exhaust temperature?
Cylinder?
Yeah. Which cylinder has the hottest exhaust temperature? I can see Romero laughing.
Depending on what type of engine. It's always.
Just looking at those, you got high pressures, low pressures. Which one's the hottest one? Who knows? They're all the same. So here's, they're going to be close. They're not exactly the same, right? But where we put our temperature probe is right here, not right here. So can you balance off exhaust temperatures? You can try, and boy, do we try, right?
Balance and then adjust for your exhaust temperature.
Yeah, you can do that. Yeah. So this is why it's really, really hard to balance off exhaust temperatures, okay? See how those peak pressures are all different right there? But right there where we're actually measuring it is pretty much the same. Here's how you know. Those are all, that's this engine right here. Had a good variability from 550 to 700 almost. And the temperatures were pretty much all the same. So what good are exhaust temperatures then? Dead or alive? That's all I can use them for. And really say if something's going on. You got a dead cylinder and a live cylinder. Now, you've all done it. Oh, that one's cold, 200 degrees. Oh, let me go open up a little fuel. And will it go up? Well, then you win, right? So, not saying don't do it, but you don't know what that did to the peak pressure, right? But you might have woke it up a little bit, shot it with some caffeine or something, you know? Okay. So I put this in here just for that knowledge. I realize it's easier just to look at the exhaust temperatures, but you're not changing the peak pressures or the horsepower much. So you're not fixing combustion, if that helps. Okay. Here's one. This just happened a few weeks ago. Pocatello 2. So these are all the traces we took on, that's cylinder number 4 right there. And you see how there's a couple high ones right there. The average looked pretty smooth. But when we looked at all of them, we saw there was some erratic combustion or detonation, whatever you, unstable combustion, whatever you want to call it right there. And look at the exhaust temperature on that. It's exactly the same as the rest of them right there. Okay. So this was on the resonance. We diagnosed that. I think Cody went out there and he said, yeah, we got something wrong with that fuel valve, right? This also happened to be higher than the rest, this fuel valve closure. So there's 2 pieces of evidence right there. If I'm just using this, I don't get the answer, right? Okay, does that clear that up? Makes sense? Questions, comments? Okay, should we move on to compressors? Okay, here's an animation of the compressors right here. They're double acting, which means you get work or action on each side of the piston. Okay. So you've got expansion right here, suction valve opens. And then it recompresses recompression. takes it up to discharge temperature, discharge valves open, and repeats the process. Okay, what are these dotted lines? What is it, Ramiro? Theoretical. You guys know I care about this, but should you guys care about it? What does that tell us? Yeah. So one glance, do you see how those dotted lines line right up on the solid lines? Instantly, I know that's a healthy compressor. How cool is that to know that right off looking at it? So that's because those dotted lines are lined right up. If these dotted lines are something we put in the software, and all they are is the engine geometry of the volumes that are in there per load step. So there's going to be a matrix of them for each cylinder, for each load step. And those are in there. Those were done before I arrived, but I've also refined the heck out of them and put them all in there. And then this is what we verify with the Windrock and the resonance is when we read this, we have indisputable evidence that our calculation on those blue screens is correct. Because gas control's trading off that information, right? Every once in a while, these will be off a little bit, and we'll either have to check our calculations, which we're pretty much done for Northwest Pipeline. We've double checked those and triple checked them. Doesn't mean we shouldn't always look at them if something changes. But if they're off, then we need to question something. Before I move to the next slide, what's this? Valve, yeah. Is it good or bad? It's not great. Yeah, that's a good way of putting it. We say good or bad, but a lot of times there's stuff in the middle, right? Compared to the other ones, what's it doing? Yeah, it's leaking. Good point. I might have one of those pictures. So is that a suction or discharge valve? Yep, yeah, so you can look right there and cheat, or you can count down. But, or if you know where it's leaking, you can say that's probably a discharge valve, but you're exactly right, discharge valve head end, okay? So, see that difference in the lines right there? That's probably the difference in the leak right there that we're seeing on the dotted lines versus that. It's pretty close, okay? Real bad valve, you'll see the difference there. Okay, here's the worst valve picture I could find with some pretty good valves that I could find. Actually, this is the same engine. So good versus bad. So when do you pull a valve? Well, yeah, okay. This right here, I mean, a 5-year-old can just look at that and say something's wrong, okay? Well,
Color.
yeah, didn't know how to color, that's right, yeah. Okay. So that's screaming at you, but there's stuff in the gray areas that you have to make judgment calls on, okay? So to give you an idea of why we should change valves, operator at this time was rebuilding old style valves, so the metal ones, metal plate valves, and there was just a goodie box over the years of spare parts and just kind of rebuild them. And this particular operator called those new valves. And I thought, man, that's what a new valve looks like. I thought he had bought new valves. And I come to find out with a little bit of talking that it's just rebuilding old style valves, right? And so we budgeted for new valves, and then we did a cost benefit analysis. And this particular station with 4 recips gained 13 million in additional flow, just in efficiency. And so the math on that worked out to a 2-day payback. So you buy a valve and in 2 days, you've made up for it in flow. Okay. So I know we're all operators here, but you can actually be on the money making side of Williams by running your assets efficiently. And this is one of them because we get paid by a throughput. With an asterisk, we get paid at the meter stations, right? But it never gets to the meter station if it doesn't go through an engine.
So what, valves you would rebuild, like when they have machine problems, they were good surfaces.
They were like 25 years old, and they were just an original OEM design.
Oh, okay.
Instead of new poppets with Teflon and the PEEK material and all and new springs and everything like that. Yeah. In general, they say that a new poppet valve built in the last 5 years or 10 years is 3% more efficient than the 10 years before it. So it behooves us to have new design of valves, and they just have better machining, better materials, and also better flow analysis and computational fluid dynamics to make these valves better. And in my opinion, most of the valve manufacturers out there are pretty good because they've all learned from each other and they're trying to be competitive. Okay, Romero mentioned this. So when does a discharge valve leak? If I'm looking at my head end right here, so pressure is going down, suction valve opens, and then it recompresses, discharge valve opens, excuse me, right here, goes here, discharge valve closes. And so from here to here, a discharge valve is supposed to be closed. So simple question, does a valve leak when it's open? Okay. It doesn't, but a valve can struggle while it's open. It can flutter, or, if there's problems, it can struggle. On the other side right here, so this is where a suction valve will leak if it's supposed to be closed. Look at that one right there. I mean, that's a nice football pattern, and that's discharge number 4, and it's leaking when it's supposed to be closed. So you're going to change that out probably. I don't have temperature right here, but if you put a temperature on that, or you put your hand up to it, you're going to say, hey, that one's hotter than the rest. So you don't even have to do this. This just confirms it. So suction leak right here, I'm looking at this blue trace right here. So right here is where the suction valve is supposed to close, or excuse me, suction valve opens, closes around here. And so a suction leak would happen around right here. So where those footballs line up actually matters. So once you look at a few of these, you're like, oh, that's a suction or discharge without the labels, but it sure is nice to have the cheat, right? Another way you could look at it to see this pressure right here. The pressure struggles to get down based on what it should do. See that little difference right there? So it is slower at getting its suction pressure because of a discharge leak. Okay? Questions? Those are discharge valves. Pretty easy, pretty simple on those. Those ones, you can have a high rate of success in diagnosing those. So the engine side, I will say this. Engine side can be tough. That's hard to understand, right? There's a lot of moving parts. Compressors are easy. And lucky for us, compressors are what make us money. So if we can get those dialed in, that's the golden egg that the goose lays, right? We want that golden egg. Put that money down the pipeline and then we all get paid. Okay, so here's what a pocket unloader not actuating or broken looks like, okay? So do you see that difference in the dotted line versus the traced line, the solid trace? I just put this human here to say, hey, if you're looking at it and you don't have it memorized, the head is at the top. So head end, crank end. Maybe I didn't mention the names of the cavities that produce the pressure. Head end is out on the end and crank is closer to the crank. When I'm looking at this right here, head end cavity, crank end right here. The only difference in volume is the volume that rod takes up. Okay. So immediately I see a difference right here. I could say, oh, well, that's probably that valve, but is that valve really causing that? So in the software, I move that load step to another load step lesser. So maybe from 9 to 8 or something like that. I guess in this case, it's 6 to 5. And magically that line lines right up right there. I'm not doing the math at this point, but that shift in volume is exactly 1315 cubic inches, shouldn't be square inches, cubic inches. So that's odd. And then it's also happening right here. So what's happening is the pocket is not shifting in volume. This thing right here, that's what I mean when I say a pocket or an actuator. It has a plunger in there, and even if there's an indicator, it's disconnected, but or the solenoid's not working for whatever reason, that is not going back and forth when it thinks it is. So why is that a problem? Yeah, you have a difference in flow, and the PLC is like, well, I don't know it's broken. I'm going to calculate the flow. Gas control is making decisions off that flow. So the difference in this particular valve was 3.6 million standard cubic feet per day. So the customer thinks they're getting that. Gas control thinks we're flowing that. And if you run the math on that at $2.50, that's $1.7 million per year in lost throughput, just due to that unloader, okay? In this particular one, if I've got the engine right, there was just an air line going to the actuator that had a leak in it. So we fixed it with duct tape. Just taped it around, and it was just not getting enough air pushing to it. So oddly enough, at this particular station, we also had, I think, an alarm that said you've got a leak in the pocket air actuator, right? So many indicators on this one. So you fix that, and then you're gaining 1.7 in throughput, okay? And you may not know that until it shakes out at the meter stations, and we're not going to do that math, okay? Now, what happens if the operator had that in remote auto, and then the load shifted, and pocket step went down or up, and then I'm looking at the data, I'm like, oh no, you've got a broken actuator, right? That's good news, maybe it's not broken, right? But now we have to double check, okay? Clear as mud? All right, so that's what that is. For Northwest, and I'll ask the Mountain West guys, apparently we do it wrong. We're different from everyone else. We call load step zero low torque, and we call high torque load step 9. So loading up, moving higher in load step is higher torque for us. Apparently everyone else does it the opposite. Okay. Okay. All right. At least we're standardized. Somebody at a class said us and the Russians do it that way. Nobody else does it. So.
I feel like Greasewood and Aiken are different.
Are they?
Two of our high-speed stations up there.
Okay. That'll be confusing. Yeah. I think this is Green River, actually. Yeah. Yeah.
ACI or
Yeah.
Randy Anderson and some of ours.
Okay. The point is just know which way is up and which way is down, because that'll confuse you like crazy. Okay. So that was an easy fix that was worth $1.7 million. Okay. Now what happens if that operator goes to his manager and the manager says we're all out of money? At that point, the operator should do the math and say, well, we're losing $1.7 million a year, or put it into days and say, hey, that's 20,000 a day, and see if that'll wake up your manager, right? So how quick are we to change a spark plug? We're turning the engine off, right? Well, how quick are we to change a valve or fix an actuator? Well, these guys are like that, you know? Sometimes we wait till the next 8,600 hour or until we have budget, right? But should we? So what's William's job? We work to make money. So if we're in the business of making money, which maybe some of you work for fun, but if we're making money, then we take care of the golden egg. Yeah, these guys aren't getting paid over here. Okay. All right. So that's compressors, fairly simple, right? Engine economics. So for those of you in this room, simple math, right? We don't want to get complicated. What does 1 million cubic feet per day cost? So when we talk about 1 million cubic feet per day, what does that mean to us? Bottom line, right? But how does it correlate, right? So when you're looking at it, you take your flow, 1 million or 1,000,000, 6 zeros, times it by a BTU factor. And if you don't know, just use 950. And then for transmission, our tolling cost is about 39 cents per million per MCF. That's about what we make as tolling. So we don't own the gas, right? We just charge the tolling fee. So that's about $370 a day. And what we get to pocket for 1 million standard cubic feet per day, okay? So
What was the term you used? Tolling?
tolling,
Just like toll.
yeah, a toll booth, yeah, good point. Yeah, I might have glazed over that. Yeah, so that's how transmission makes money is we charge you to go through our gate or use our pipe, right? They talk about firm transportation. We're just transporting your product from one place to another. And it's different parts of the pipeline are different, but it averages out to 39 cents. Mountain West will be pretty close to that too. G&P and midstream, they actually own the gas and it's true dollars. What I mean is it's not 39 cents, it's Henry Hub price. I'll show you that in a sec. Okay. So all that math works out and that's what it comes to be. So here's how the customer looks at it. So if you're working for G&P or midstream, and here's what, this is how our customer sees 1 million. Okay. So let's say the commodity price is $2.72. That's probably around that today or something. That's $2,500 a day of product that we have agreed to ship to our customers. And if it's running 365 days a year, that's $1 million. If it's half the time, it's $500,000, right? So that's just 1 million. So in the wintertime, you know, this is 2022, commodity price went up to $6. Now the customer is paying or buying $2.3 million per year in product. That's how much that costs, just 1 million. So that's $6,000 per day. So the commodity price matters to the customer. We don't care if we're tolling it, it's still 39 cents. I don't know if you guys have heard Alan Armstrong say, lower prices sometimes help us because people are willing to ship more. And we get to toll it at 39 cents. So that's one of our business hedges is when commodities are low, our transmission business might do better. When commodities are high, our midstream and G&P business might do better. So it's kind of a hedge. Okay, do we care about fuel? This is rhetorical. Doing good on time? Okay. This is rhetorical. Do we care about fuel? Because you're good people, you care about fuel. We as a company, do we care about fuel? Kinda. Well, let's run the math and see if we should care about fuel, okay? So remember, fuel is the part that gobbles up the money and the fuel and the horsepower and makes the horsepower. So we want that to be as low as possible. So this particular engine that I had back here, this one right here, Green River engine, Cooper, 6-cylinder, 262,000, not million, thousand standard cubic feet per day, times it by the chromatograph value, 39 cents. So if we were to push that down the pipeline, it's $100 a day in gas that we use. So that's pretty inexpensive for a big engine. Right?
So your PTO calculation on that one is the elevation change where the compressor's at?
This BTU, this is just the chromatograph, and it was just live at that time, 942. And this is lower heating value. Higher heating value, lower heating value. The difference is in combustion, you don't get to use the condensation. You ever seen at a stoplight where a truck has water dripping out of the tailpipe? His buddy didn't pour water in it. It's part of the combustion that's dripping out of the tailpipe. And that energy and condensation of the water you don't get to use. So the higher heating value is going to be 1050 and the math is 90%, 90.1%. And so they just say 10% less is your lower heating value. And that's what you don't get to use in energy. So that's why we use lower heating value in all our calculations. So that was just a live chromatograph reading for that engine right there. So 39 cents, $100 a day, 17,000 a year if it's running half the time. So tiny money. Do we care? Yeah, it's money. But check this out. Here's how the customer sees it. So the customer pays us $670 to burn that fuel, whether we're efficient or not, right? So 122,000 a year, they pay for our fuel costs. You guys know that, right? We don't pay for fuel. Okay, so do we care about compressor flow? Again, this is a tiny recip, what we call tiny. That's 83 million a day. So 262,000 a day, or I'll just say 0.26 million compared to 83 million. One number is way bigger than the other. So our tolling capability is 30,000 out the door that day. That's what we stand to gain. And if it's running half the time, that's 5 million a year. So that one engine throughput's 5 million a year in throughput. Okay. So times that by a transco station of 10 right in a row, or 4 in a row or something at some of our recip stations. So that's what we stand to gain. That's our tolling charge. But look what the customer value is. So they bought it. Hopefully they buy low, sell high. But the customer, if they're looking at it at $272, that's 38 million a year, and it's $212,000 of product going through that engine. Okay. So do we care about fuel? Does the customer care about fuel? It's lower. What we really care about is throughput. That's where the money's made, right? So it's just object cash flow. What's going in versus what's going out, right? So something confusing. You hear BTU, you hear decatherm, you hear million BTU, you hear all those things. Just know that 1 million BTU is 1 decatherm. Okay. Another way of looking at that engine is what's going in to the engine is 0.26 million. What's going out is 83 million. So that's 1 part of fuel to 317 units of gas pushed out. Okay. So a pretty good ratio. That's 0.32%. Not 3.2%, not 32%. It's 0.32% of what it's burning versus what it puts out the door. To me, that's really efficient. Okay. It will never crack 1% unless you are doing something bad, unless something's really, really broken. Okay. So that's a pretty good little setup right there. Convert it to cash, $600 in, $220,000 out. Who would like that investment, right? Okay. So the money's where? In the throughput, which is in the, yeah, okay. And you see my little asterisks. If I got measurement folks in here, they go, if you don't have meter stations, you can't make any money. So, and then we go, well, if you don't have engines, you can't have anything at the meter station. So we make money at the meter stations, not at the compressor station. If you were to look at the compressor station inside the fence as a cash register, this is how you analyze it. Okay. Hopefully that makes sense. Just out of curiosity, a turbine. So I realize this is a recip training, but we're just going to compare the costs of a turbine. So a Solar Mars 90, a much bigger engine, much bigger horsepower, but what's going in is 2.3 million in flow, and what's going out is 512. So almost double the amount of flow, right? So that Clydesdale might look real pretty, but look what the Clydesdale's pushing out. Look at the Clydesdale's dragging. Right? A lot more than the donkeys are in the Super Bowl commercial, right? So that ratio is 1 to 219. So yeah, it's gobbling more fuel, but look how much it's pushing down the line as well, okay? Look at that ratio right there, 0.46. So it's still less than 1%. So we go around and say, oh, turbines are less efficient, but not by far, okay? 0.32 right here. And 0.46, it's still under 1%. Okay. So in math, $6,000 gobbled up in fuel, but $1.3 million sent down the line per day. Okay.
Put the labor with it, labor and materials.
Yeah, labor and materials are not included in here, but yes, if you put that in there, then it costs more, doesn't it?
On a recent,
Yeah. Just cost and maintenance, right?
Yeah.
Yeah. And then with solar, we just call solar and they're free.
oh, yeah.
Yeah. So this is just a comparison, not to say one's better than the other. I'm pro Williams, not pro Recip or turbine, right? Again, this is a Recip class, just something interesting. This is Sumas number 7. You can see all these points on Don's training. These points ran off the map, and that's to say inefficient, okay? We re-wheeled number 8, number 7 didn't get it, with a wheel that looked like this. That's another look at what happens. They just changed these wheels in here, these discs, so to speak. And here's input versus, or fuel per throughput. So this is Sumas station right here. So these are the old Clarks right here, or the Ingersoll Rands and the Clarks. They're right here. Low fuel, but compared to what they're throughputting, pretty good. These ones right here, this is the turbine Mars 90 that's most efficient. This is the one that got the re-wheel. And here's the Mars 90s that are re-wheel candidates. I'm only showing you this because a re-wheel can save 23% in fuel on a turbine. And so all we talk about is methane, 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 methane. And our biggest portion is from what's burnt, not from what's leaked when you look at that sustainability report. So if we re-wheel, we actually produce less CO2e or methane that's combusted. And that's only by running efficient. Go ahead. Oh, good question. So the question is, what's a methane slip for recips? A whole lot. And a turbine is almost 0. So I think it's more like 16 to 20%. Yeah, it's high. So that's one of the reasons when we're looking at combusting with NOx and methane slip, turbines have very little methane slip, almost to 0. Yeah, and unless you really lean out or put some nice controls on a recip, which costs a lot of money to retrofit, then you're not going to get that. You're going to still have a little bit of slip, but you lessen it a whole lot. Thanks, Ryan.
Right. Well, do you get to see the cost per million cubic feet on maintenance?
No. So the question was, do we get to see the maintenance cost? And over the years, we've done lots of efforts. And about every 5 years, someone goes, let's calculate and put the O&M maintenance, because you're thinking on the right lines. You're thinking all the money, not just the cash register.
Yeah.
Yeah, you're thinking maintenance, labor, everything that goes into it. And we had it at one time. And then it was in our OMS system. And we had somebody in Mike's group that was working on it and putting O&M costs in on top of all our efficiency stuff. We were real close and they blew it away. And then we went maximal. And so the proper thing to do is to actually add all those costs in. It's just really hard to get those O&M costs and get it right.
I brought track of your maximum.
Yeah.
On a particular unit.
Mm-hmm. Just my opinion, the company that does that and gets it right and tracks it and acts on it is the company that's gonna win. It's playing the game right, because it's like the holy grail. I've tried to find that stuff and I found it, and then I'll do a spreadsheet, but it's not a live report. You gotta question these numbers over here. Somebody puts theirs in different and everything like that, but would be nice, maybe one day. So, but he's right. That's the way you should be looking at it. There's O&M costs that go into it as well.
So we have access to your PowerPoint.
Mm-hmm, yeah. Yep. So I'm winding up. So here's how you look at it. money in, money out. But things take maintenance, right? But we want that to be as small as possible. Here's another way of looking at a turbine. Okay. Oh, yeah. Yeah, so the comment was made that time to service for like new data centers that want it now. I mean, everything we do, we wanted it fixed yesterday or we wanted more throughput now, right? Yeah. Yeah, you could be years out on a turbine and then a recip, like maybe a smaller Cummings one or something, it'd be right off the shelf. Same with some of our cats, might be a little faster, I guess. Yeah, that'd be a good consideration as well, too. Mhm. Yeah, it depends on how much Bitcoin is. Okay. All right, so my final comment, I'll just read it. This is from Stephen Covey in the 7 Habits. If you adopt a business that focuses on golden eggs and neglects the goose, you will soon be without the asset that produces the golden eggs, the engine. On the other hand, if you only take care of the goose with no aim toward the golden eggs, you soon won't have the wherewithal to feed the goose. Okay. So that's pretty much all I've got. So let me open it up to questions or comments. Very good. Okay. Thanks for sticking with us. We are officially done. So you guys are all free to go. Thanks for coming and we'll do it again next year. Mhm.